Hello everyone, welcome to my presentation, Multiple Energy Assisted AFM-Based Nanomachining Processes and Applications. I'm Jia Deng, Assistant Professor at Binghamton University. So today I'm going to first briefly introduce the common nanomanufacturing techniques, and then I'll talk about Multiple Energy Assisted AFM-Based Nanomachining, and then the application, rapid fabrication of SERS substrates. So first of all, as we know, nanomanufacturing is a manufacture of sub-100 nanometer patterns, components, devices, and systems. And we need multiple different and functional nanofabrication techniques to support all those applications. So there are some existing nanofabrication techniques available, including extreme ultraviolet, X-ray, electron beam lithography, ion beam lithography, and the recently emerging atomic force microscope-based nanolithography. As we know, EUV is the next generation or current being used for fabricating sub 10 nanometer features to fabricate CPUs, etc. And the electron beam lithography has been used for fabricating masks for photolithography, and ion beam, the same thing, has been used for fabricating different arbitrary patterns. However, there are some limitations for them, such as scattering effects, so it is difficult for them to fabricate very close pitches and three-dimensional nanostructures. And as for atomic force microscope-based nanomanufacturing, it has many different variations, including mechanical direct scratching, thermomechanical material moving, deep pen, electrostatic nanolithography, etc. And by comparing all these nanolithography techniques, we can see traditional atomic force microscope-based techniques are cost-effective, comparing with EUV, electron beam, ion beam. However, it usually involves a large normal force, which resulted in quick tip wear. So we kind of developed a vibration-assisted atomic force microscope-based nanomachining. So as we can see, at the center part is the nano vibrator. It has X piezo, Y piezo in the plane. So when it's vibrating, the center pillow is going to vibrate in a circle way. And then there's a Z piezo that placed underneath the sample, and it has this function. And so the mechanism is like this. The left figure A and B shows the XY vibration mechanism and the function. So because the X and Y piezo pillow that vibrates the pillow, so the when the AFM is moving, when the tip is scratching on the surface, the sample is vibrating in the circular fashion, which increases the nano change width when there is a single machining path. And in terms of the C and D picture, it shows the function of a Z vibration. When the frequency is very high, it dynamically frees the cantilever, so the cantilever can indent deeper into the sample. And as we can see, this is a nanomachining capacity that can be achieved by previous setup. So as we can see, if we increase the XY amplitude, we can increase the width, and also we can increase the we can maintain the Z vibration. We can increase or maintain the depth by changing the different Z vibration, or maintain a certain Z vibration. In that way, we have control of the implant feature and Z directional feature. So we can fabricate arbitrary three-dimensional features and patterns. So this is one example that shows the nanomachine results and the quality. This is the upper part. Upper left is the original image. The bottom left is fabricated results. The dotted lines are the original features. The solid lines are fabricated by atomic force microscope nanomachining results. There are some overlaps and some mismatch because of the tiny features. The tip may not be able to indent deep enough. So there are some limitations in terms of force, so the tip can be weared pretty quick. There are some existing literature shows using the heat assisted. So we are evolving from the vibration assisted. Then we actually add a heating template underneath the sample, so to further decrease the normal force. So we can, because of the smaller force, we can even use a contact tip with a very low spring constant to do nano manufacturing. As we can see, because of the temperature involved, there is a increasing adhesion force. But with the vibration, we can efficiently decrease the adhesion force between the tip and the sample. So this is the results. As we can see, if we apply very small force and different sample amplitude, sample temperature, and we can actually tune the feature depth. And also, as we can see, we can use very small force as low as 50 nanonewton to pattern features with the sample temperature of 42 degrees C. So that's about the nano manufacturing process. And one application we can do is SCRS substrate. So the SCRS is surface enhanced Raman spectroscopy. So common Raman signals may not be very strong, but with patterned substrates, the signals can be magnified. So our fabrication and the characterization process are here. First, we coat 80 nanometer PMMA on the silicon substrates, and then we do patterning on the PMMA by our AFM-based nanomachining. And then we transfer the PMMA on the silicon by RE, reactive ion etching, and then we coat a gold layer on the patterned silicon. And after we get the SCRS substrate done, we deposit some probing molecules on the substrate, and we detect the problem molecules using the Raman microscope. So these are the grids directly on the PMMA by atomic force microscope-based nanomachining. So as we can see, the depth is only 10 nanometer to 40 nanometer, and the deepest can be 80 nanometers for those features. And we actually make 4 different patterns, and we transfer it on silicon and coat a gold layer. So after doing the RE transfer, as we can see, the depth are very much deeper, and that is very necessary for a good SCRS substrate. So we make 4 patterns. This is pattern 1, pattern 2, pattern 3, and pattern 4. So pattern 3 has some over etched, so the pillows or the features is kind of almost gone. And as we can see, this is the result after we deposit some probing molecules R6G. The feature 2 has the highest the enhancement factor, and as we can see, when we compare the feature the pattern 1 and pattern 2, it has a similar depth, about 600 nanometer, but the pitch is with a smaller pitch or dense features, the enhancement factor can be better. And also these two are not as good because the depth is very small. So brief summary, we use vibration and the heat assisted nanomachining process. We can fabricate arbitrary 2-dimensional and 3-dimensional nano features, and because of the heat involved to decrease the shear force of the thermoplastic material samples, we can further decrease the normal force to about even 50 nanonewtons. And we use this process to demonstrate the application of fabricating SCRS substrates. So the enhancement factor can be achieved is about 3.1 by 10 power 3. And as we can see, the density we can detect of the R6G is very low here. So that's all my presentation today. Thank you very much for your attention.